Hello everyone. Here's the thing. I'm thinking to implement a branch predictor on my RIS5 assignment. And while I'm doing that, I try to wrap my head around. And I was thinking, while I'm trying to do this revision or revising to try to wrap my head around, I might as well record a video. And if anyone is interested in building a branch predictor, yeah, so cool. Um, so um, I'm gonna spend maybe 5 minutes just talking about like the background and the motivation. So back into the very basic pipeline, you have the following stages, which is the fetch, decode, execution, memory, and write back. And someone here, you have the branch early, and also you have a branch main. Okay, maybe I draw a little bit too small. But then recall that if you have a branch, pretty much you have the following. You have branch equal, branch not equal, and you have something like branch less than, and then branch greater than equal, and then also the unsigned version as well, unsigned version of them. So this is basically just asking equal, not equal. Oh, okay, I'm just gonna draw equal, not equal, less than, or signed or unsigned version, signed version, and then oh, sorry, and it'll be greater than, equal to, that sort of thing. So let's actually talk about some stuff. So you know that when we go back to the AL, back to the spring term DECA last year, we talk about how when you construct these two, you pretty much need the CMV flag. And the CMV flag only generates from the hardware for ALU. So this is the main reason you put the main here. So for instance, there's a separation between them. So there's an addition here. Let me clear my head again. So there's an ALU here. And ALU pretty much has this adder built in there for the app sub sort of components within it, and you can then use this synthesizer will pretty much, if you have the branch module, try to handle these two commands. It will basically generate the CMV sort of, not flag, because this is the 32-bit instruction, so it doesn't really need a storage to store it because the instruction is long enough to put the branch's address in. But then the CMV sort of indicator, I'm going to use indicator instead of the word flag because they're a different idea. Flag is basically a D flip-flop trying to store. So for the next instruction to be put in, for the next branch instruction to check what sort of address I need to go to. So yeah, so well, these two are actually a bit interesting because if you consider the actual hardware, this is basically just decoder type. You can just build like a yes or no by having a decoder. And equal or not equal, you can pretty much just build it from comparator. And comparator is really easy by just having a bunch of XOR gate connected together. So to summary, this is very hardware inexpensive, so it's very cheap to build the hardware. And this is, well, meanwhile, quite expensive because say you have a 32 and 32-bit, then you essentially need the 32 and 32-bit adder to generate this CMV indicator, while the N and Z are quite easy to generate actually. Yeah. So because N, I just pretty much have to fetch the MSB, and then the Z, I just need to have a big comparator, which is quite cheap in terms of the hardware cost in terms compared to another additional adder. So I'm gonna set up the scenario as such. I'm gonna have an early branch and also the main branch, which early branch will mainly be deal with BEQ and BNE, and then the main will be pretty much be dealing with BLT, BGE, and the rest. So this is what actually happening. So you pretty much have another two sort of drawing back to your maybe your PC or some sort of mocks to resolve what your next jump address going to be. Okay, so this is pretty much the problem setup. There's also an alternative way. It's basically just to merge every BEQ and BNE back to the main. And another question, just not really relevant, but is how come I can't just put every main into the early branch? Because like I said, you need a CMV indicator here, and then having an additional sort of adder put here just to generate the CMV flag, CMV indicator, because the hardware synthesizer will tell you you need to add it here. Will be quite expensive, and then since that you already have ALU here, why not just share the cost with it? But with this approach, you definitely going to suffer from one cycle of branch bubble, for instance, for sure. But that's also fine, because yeah, it's a bit insignificant, so it's probably okay, and this is probably the best we can do. So as you can see, here's some sort of hardware trade-off between the hardware and the performance. Okay, so the problem set up as such, we have FDEMW. So the idea is that as you can see, if I use green for my early branch and also orange for my main, as you can see, these are the timestamp that where my branch address has been resolved. So for green, it has to be the third cycle where I can have a new fetch again, and for my orange, I need to have the fourth cycle to be generate a fetch again. So as you can see, there's definitely going to be suffering from this bubble, which is the branch bubble. Well, it's fine, but what if I have a simple loop, a simple for loop look like this: for I equal 0, I less than 100, I plus plus. Okay, so if I have something like this, then surely if I maybe if I just say every time maybe I have to jump back, and maybe I have to jump back, maybe I have to jump back, but then your code might think that you're going to go this way, and then they're going to mispredict, and then you ended up finding that you have this issue of flushing. And then flushing is fine, but then very frequently your code is going to suffer from like a very big amount of loop counter, and this loop counter will basically adding up all the this mispredict penalty, which is this branch bubble that you're happening. So if you have this bubbling happening, then it's going to keep suffering from that. And if you actually do the calculation, maybe from one of the worksheet and stuff, you ended up finding that this penalty added up to be quite significant. So no matter what, even though you do no matter which state you put, maybe like you say early or you put in main, you always suffer from this issue. So the idea is here. What happen if I can sort of before, because this is the case when you flush it just saying that, okay, I actually just mispredict, and then this instruction is the wrong instruction because I was supposed to go back instead of fetching the next instruction. So this is the wrong instruction. I need to flush it. What happens if instead I can sort of predict that when I'm arriving here, I sort of just knew that I am going to jump back. Isn't that kind of cool idea? So what happens if I have something here, like a branch predictor, but just next to the PC, so you will be suffering from no bubble, and then just directly fetch to saying, okay, now is this here your PC? Your PC is probably, I don't know, 1,000 something, and then somehow it just knows that, oh, once I reach to 1,000, I knew that I'm going to jump back for the majority of the time, because as you can see, this loop counter, majority of the time you're going to be like 1 for jump, so I'm going to be like jump, true, da 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 da, and then maybe like 100 of them something, or 99 of them, and then the last one will be not jump. So we can pretty much have two ways of solving this. One is called the software, and then the hardware. Okay, and of course we're hardware engineers, so we're going to choose the hardware approach, but just talk about a bit about the software approaches that you can have some sort of indicator in your assembly code or maybe your C code to say that, okay, if I have perhaps if I know that, okay, if I give my assembler know that, okay, every single time my policy is that I'm going to have PC equal PKs plus false as my sort of branch not taken policy, then it can somehow go here, right, and generate that to indicate that, oh, look at this, the majority of the time it's going to be true, isn't it? Majority of the time it's going to be jump, right? So it can sort of rearrange the assembly code to allow that this policy to be true. So this is what you call the software scheduler, so software scheduling. Software predictor or something. Yeah. So I think so this come in quite cool. Like if you can build like a compiler that just sort of know this indicator, and then know that your hardware spec, and then just somehow match them together, which is nice. But then we're hardware engineers, so we're gonna build hardware instead. So if we talk about hardware instead, how do we actually use this? Is that what happens if you can just have like some sort of memory? So the setup is such, somehow, okay, first of all, I know that there is a branch here. So maybe I'll just use a indicator to say that there's a branch here. So I just tell that, okay, careful, every time I come to 1,000, there is a branch happening. I don't know which way to take, but there will be a branch. So yeah, so maybe I'll need to have an entry and say that, okay, I'll need to have entry just to store that this address. I have to be very careful when there is this address. So first of all, I need to store the address. And then secondly, what happened was maybe I have to have an indicator, so to have maybe 1 bit or 1 bit or something to say that, okay, what is the last time I did it? So if I can just simply look back and say that, oh, what's my last policy? And I can simply just generate that. I can just basically look at that policy and just try to do what I did last time again. So maybe, okay, for maybe I initialize as n, and then I go here, and then there's suffering from a branch penalty. So I can say, okay, the next time I should actually jump. So I just update it to be jump. And then as you can see, true, 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 da, da, da. And until here, I suffer from again. But then it's good because my accuracy is now like 98% or something. So if I have this 1 bit indicator, isn't that sort of nice to say that, okay, I can just simply look back and do stuff. But then there's another case, which is like for I equals 0, and then I maybe take remainder equals 0. I plus plus. This is often a really, really actually, sorry, not this one, this one is a bit weird. This one probably you don't see that often, so maybe I'll use a different one. Okay, I can't think of a branch just at the moment, but let's just think about what actually happening. So is 1 bit enough is my question, or how many bit of storage do I actually need? Like, because so far I only have 1 bit, and what does 1 bit means? 1 bit basically means that I am storing the last result because that last bit is like, oh, 0 for not jump and then 1 for jump. So that pretty much just tells us the last one activity. And then the natural question comes into that, is that the best design choice? And do we need to increase any do we need to increase like the record? So sorry, not this one, not this one. So yeah, if we take a look at what's maybe you have something like this, and I say not jump, and I say jump again, not jump, jump again, jump again, jump again. This is probably quite often as well, right? Because if you have like a for I equal 0, I less than 5, I plus plus, and then maybe you have another for loop, and then say for j equals 0, j less than 10, j plus plus, something like that. So you can see that this sort of jump and not jump pattern is quite often. Yeah, so this is what happened. So look at what happened if you take a look at, okay, so I'm here, maybe I initialize as n, not taken, so I suffer from the miss penalty, and I just say, okay, the next time I'm going to jump, it's going to be t. So match, 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 match. Oh, over here, because last time it was a t. So over here now I got mispredict, so I'm going to circle it. So now I know that I have to update to n, but then over here again, I mispredict again, so I have to update to t, and then I have to keep going. So as you can see, you can sort of try to find that now every single time when there is a transition between the t to n to t, there's a transition between t to n to t. This thing over here will cause 2 misprediction penalty. So is there anything we can improve that? And the idea sort of comes in with the idea of debouncing, which is, say if we have something like this. So say if we have a pattern like this, and this is probably 1 bit, and I can say, okay, I'm going to set my tolerance to be maybe 2 bit. So what if I can just smooth this out? So like maybe in your sort of previous lecture we talk about this noise sort of recover from the noise where you have the debouncing, right? So if you have a button that has multiple debouncing issue, which one do you know that is the actual press of your button? So you're gonna increase on your hysteresis. So the idea about hysteresis is that maybe I'll wait for like 2 bits, and then if 2 bits is like enough, 2 bits is probably enough for me to change the state, but 1 bit is probably not enough. So in that case, I will not recover. I will sort of restore from my sort of remove my error is what I mean. So this is the idea where it comes to the bimodal in the final lecture. In the bimodal had the following FSM, which is 0, 0, 0, 1, 1, 0, 1, 1. So you sort of say, okay, every time. So this is called the strong, not taken, and this is weak, not taken, and this is weak, taken, and this is strong, not taken. And you can see the reason why. So when this, so let's draw the state transition. So it's like, okay, every single time when I have a misprediction, which is in this case a non-jump, an actual jump, while it predicted as a strong not jump, then it has a transition towards the weak end. Well, otherwise is that, or if I predict not taken and it's actually not taken, then I'll become a strong not taken. So the you can see that the state transition sort of looks like this. Hopefully, yeah. So the number I'm written here is that the actual result, whether it's taken or not taken. So if I have 1, and if I have 0, and if I have 1, 0, 1. So as you can see, you can try to pause it and try to work it out. What's the idea about the state transition here? Okay, so that's pretty much the strong not taken, weak done. So that's bimodal. And bimodal, you can see that now, if you try to work this problem again, you can see that now it solved the hysteresis. Because if we try to go back to this specific case where you have the T and T, T to N to T, that sort of transition, what happened was you're gonna say this is the strong taken because previously are all strong are taken, so it's gonna finalize into the settled in the strong not taken, sorry, strong taken. But then once you go to the strong taken, and then the next one say, okay, it's not taken. So I say, oh, it's not taken, and then so now my state become become weak not taken, weak taken. But then the next one is going to be it's going to predict it as taken again, and so you can see that the misprediction only suffers this n, but then the t is still like I only going from strong taken to weak taken, but I still predicted as next one is going to be a taken. So in this case, I only have misprediction of 1, and the bimodal actually essentially turns out to be quite good because of the hysteresis. And of course, you can see that people will talk about some sort of sometimes people say that you can use like a bunch of different bits. You can increase to 3 bits hysteresis or maybe 4 bits, but up to your design choice, really. But to be honest, I think bimodal works the best. I don't know. So yeah, I'm gonna take a look at. Okay, so we kind of talk about here. So I'm gonna extend this to be a 2-bit bimodal indicator, and maybe it will be a, for instance, maybe it will be a weak not take weak taken, and always you just take a look at the MSB to say that okay, this is actually indicating T or not taken. Yeah, so that's pretty much the setup. So now we summarize it as we need an address to memorize the stuff and also some sort of indicator, and this is what this is one of the very interesting paper I quite recommended to read. So it's actually called Combining Branch Predictor by Scott McFarlane. Why is this interesting? Because actually, with a bit of ChatGPT and also the understanding, you can actually see what the setup looks like. So as you can see, this is what the previously what we sort of think the setup should be, which is 1, we're going to need address to be somewhere, some sort of indexing between your bimodal, and maybe some of the, so this selects one of them. So this is the MOX selecting one of them. And then over here, you might be a 2-bit number. And then this 2-bit number will pretty much be like, oh, 1, 0 or something. And then you can just take a look at the MSB and then so this is predicted taken. So if I want to predict, I'll just fetch the number out. But then surely later on, you're going to have the actual branch prediction. And because remember how like back in here, your actually branch prediction will actually be resolved. What do I mean by resolved is like, it's prediction, so it can be wrong. So how do I know that whether my prediction is right or wrong? Is that when you actually gone to the early stage or also the main stage, I actually check, okay, this is my following register and this is the actual results. And at this point, my branch prediction is resolved, so I can actually know what the result was. So I'm back to this stage where this is basically sorry, this is basically just like I'm taking this for prediction, and then over here, back to here, when you have the actual data, now I can update. So remember how we have this, sorry, not this one. Remember how we have this state transition. This is the update part when you finally have this result come in and you can say that, okay, now it's time for the transition. So it's just about read and write. Read is like, okay, I'm reading the value from there. I'm going to predict. And write is like, okay, my prediction is complete. Now I'm going to do a state transition. So for this to be updated. But then here comes the question is, this is actually not the best type of branch prediction. And the reason comes in why. So if you actually consider the behavior of bimodal, if you think about it for a sec, you're going to end up, it actually contain this, it actually have this sort of implied sort of connotation between it is the average. So pretty much I'm talking about hysteresis, and I'm talking about like this state transition, like transitioning between all stages. For instance, this stages, it will basically iterate through all of them and it just keep like swapping around. And you can see it's actually trying to imply something is called the average. So here's the thing. I'm actually just only know about a branch specific. So this is the PC, and the PC record has the following. And then pretty much I'm just sort of taking an average and try to smooth out the signal. Sort of like if you try to have a analog sort of analogy, it'll probably be like an integrator, sort of like a smooth circuit with a time constant that is quite large, or something like that. So you sort of smooth out this curve, but then you're taking the average, isn't it? But then something bad about this average is that what happens if you have a jump? What happens if you have a thing that just looks like something like that? No, you sort of, what happens if the case where you have like maybe your jump and not jump is like sort of in the middle, and then that in that case, if you take the average, wouldn't you be like suffering from a major sort of issue from the, sorry, you're going to be suffering from a lot from the branch prediction, isn't it? So that's a problem. So bimodal is clearly not enough, and you can see that from the reference that there is actually local branch predictor. So for sure, you definitely have to do some sort of update. So here comes the thing. Here's the new setup. You still have this bimodal here. So I'm gonna draw here. So over here, you still have this bimodal table, which again, you have this address, and then maybe one of the address will basically be like containing like 0, 1 or something like that, and then like 1, 0 to tell you indicated that, okay, what's the prediction like. But then there's going to be another thing called history table. And the history table in this case are the most beautiful thing I've ever seen. Why is that? Because just take a look at the example that's been given from the book, which is like so for a simple example, for I equals 0, I less than 3, I plus plus. And then, okay, so we know that the first time it has to jump. Second time it also has to jump. Third time it has to jump. And then next time I have to jump. And every single time when I come to this, every single time I just try to land. First time when sorry, not first time, but like every single time when I land to this PC address, I always have the following. Pattern, which is TTTN. So the idea is here. As you can see, it's actually, yeah, it's the same thing. But yeah, so what happened was you have this 1, 1, 1, 0. And the idea is that something is really, really interesting is that, okay, I'm just going to talk about the, so within this new, so we sort of said that we have a bimodal, and this bimodal will be pretty much there's an index to distinguish between, okay, we previously said that this index have to be PC, so PC sort of say that, okay, here's my address, so here's my address, and then what's the behavior of this particular address going to be like. But now this index is no longer going to be PC, and I'm going to show you another sort of paradigm, which is called the history table. And the history table is really, really interesting. First of all, what happened is it contains, sorry, it's actually called PHT, so which is called pattern history table. So the idea is that, again, you have this PC. you have this PC trying to index this and say, okay, at this very point, I will have a history table that looks like this. Maybe when I is equal to 0, it's going to be 1 1 1 0. Yeah. Wait, is it? Yeah, probably like that. But yeah, and then the next one actually will be let me try to review on, because I'm actually also a little bit unsure. Okay, so take a look at here. Every history table entry records the direction taken at the most recent end branch, whose address mapped to this entry will ends the length of entry in bits. So pretty much there is a design choice happening here, and we assume that there is a 4-bit happening, and we have to record the most recent one. So if I jump back again and then come to this address again, surely you have to be like T T N T. So because I sort of have this shift register happening, isn't it? So because okay, but how do I update this? So what actually happened here? So sorry, I actually haven't really gone through this. So assume that we don't know anything in before, and then I have no entry at all. So maybe I'll just try to recall, and basically I initialize as none, and I will say, okay, sorry, how about if I just initialize as n, not taken, not taken, not taken, not taken, and I say, okay, now I is 0, and it's going to jump back. So now what happened was I push off the first one and record the next one to be t, and then I say I'll push off the next one and then record this one to be t, push off the next one and record this one to be t, and then push off the next one and end up finding, oh, it doesn't jump anymore, so it'll be a t, and so it's going to be I equal 0, I equal 1, I equal 2, I equal 3. That's the idea. But then next time you come back to this very address, it's going to be TTTN, right? But then you initialize as I equals 0. So again, it will be like I equals 1, I equal 2, and I equal 3. That was the previous results, right? Oh, sorry, this is n supposed to be n. But then you initialize you reinitialize the I equal to 0 because you relend into this branch. So it's going to be I0, and then you're gonna start off TTNT again. So you can sort of see that this this idea of ignoring this and then containing a new updates here. Okay, so this is pretty interesting. And then what happened was, so you can see that now I have a bunch of different patterns going on. It can be 1 1 1 0, and the next one it could be 1 1 0 1, and the next one it could be 1 0 1 1, and then 0 1 1 1, and the next one it will jump back again. But what if the index, I use this one as an index right now? Wouldn't that be interesting? What I mean was, every single time if you see a 0 0 1 1 1, I will just tell you that, okay, if you have a 0 1 1 1, the next one will be not taken, because the next one will go back here. So I'll just say that every single time if you see a pattern that looks like 0 1 1 1, it will be not taken. And over here, I'll be taken, they'll be taken, they'll be taken. So again, so this is a bit strange now, is that instead I'm going to use the a bimodal, but its index is going to be 0 1 1 1, and then here it will be something like a 1 0 1 1, and then here it will be 1 1 0 1 and 1 1 1 0. So over here I will have its result maybe strong not taken, and then maybe strong taken, and strong taken. So again, we still use the idea of bimodal, because for each different pattern it can still be like, I don't know, hysteresis and some sort of small noises and stuff. But then now I try to distinguish between those. So instead of a PC, which is taking the average, now I'm specifically caring about each specific pattern. And just note that for your PC, each time I point to this address, it's going to update, and an update of the address is going to be, as what I mentioned, it's sort of like a shift register sort of idea. So I just become 1 1 0 1, and now I just look up for, okay, 1 1 0 1, taken, wonderful. So maybe next time it will be 1 0 1 1, okay, point to 1 1 0, taken, wonderful. And the next time it's going to be like I don't know, 0 1 1 1, and the next one will be 1 1 1 0, and it'll be pointing to here and say, oh wait, what was I going to say? Oh, sorry, 0 1 1 1. Okay, this one is it. And I'll say, okay, I'm pointing to this one and say, okay, not taken. So this is pretty much the setup in terms of I think if I'm not mistaken, yeah, this is probably the setup for this. So you can see over here now, this bit contains the pattern, and the pattern now pointing towards bimodal as your address. And then, yeah, so this pretty much is the lookup part. This is the lookup path. So you can pretty much just tell you what's actually happening. But then let's talk about the update instead. So every time if you want to do some sort of updates in terms of here, of course, you're going to first, again, give it back to the taken. And this taken will be the same as telling, I need to fetch in both PHT and also the bimodal table. Why is that? Because if I say the next to be not taken, I have to put a 0 here and then remove the most, not most, least recent result. And over here, maybe the 0, I was pointed to here, and then I was trying to update here, and I ended up finding, okay, 0, and then I go back to this stage transition and say, okay, 0, I'm going back to 0, 0, so which is wonderful. So that's, you can see that now two updating is actually happening simultaneously, and this is what actually happening. So yeah, so you sort of, I hope that you sort of see that the notion of having the pattern as an index for this pattern history table. And a similar sort of a similar idea sort of applies when you go through what's being called a global branch prediction, which is that there is some scenario which is because for your this is for instance, say this is your code block, so this is a piece of code of yours, and maybe at this instance you have a branch, and this instance you have a branch, and at this instant you have a branch, and there's a few type of stuff happening, which is like maybe they may be independent. If they're independent, you can pretty much just use the local branch prediction to figure them out. But what if there's some sort of correlation happening between them? So as you can see in the paper, they describe two types of pattern. And the first type of pattern is, as you can see here, I have one variable dependent on another. So yeah, so this one is a little bit hard because you sort of have to keep track of this variable. So I think you have to see this example. So you have to solve the neighboring branches, and yeah, and with the conditional correlated. I haven't looked at this table. I haven't looked at this paper yet, so I don't know exactly how you do it. So instead, I'm going to talk about. So this is the first way, and the first way is, I don't know, maybe some sort of variable tracking and a sort of mechanism. But the second one is a bit easier, which is having this nested loop. So you can have yeah. So pretty much you just actually no second scenario. Okay, second scenario is basically just for everything really, but then it's using the duplicating of behavior of the local branch prediction. Okay, it doesn't necessarily have to be this example. It can be anything, but let's just go back to our code block. So maybe over here I will have something here, and then it will probably be, I don't know, majority of the time it might be not taken. The majority of the time it might be taken. The majority of the time it might be taken. Something like that. So what if I can just keep track of this variable, and maybe majority of the time, what if I can just keep track of this table? It somehow gives a pattern as well, isn't it? So what happened was over here I'm going to introduce something. So instead of a table this time, for my global branch, I will instead have a very long k-bit register. As you can see, this now k-bit is like 4-bit, and this is actually now again like a local branch behavior, but instead every single time if I have a branch, it will be updated. So if I say there is an update in code 30 line 33, there will be update, and maybe code 45 line 45, there will be another update, and then of course I'm going to cancel the top two off, and then maybe in code 50, oh, sorry, maybe code 55, there is another update. I'm going to cancel that. So you can see that this sort of shift register behavior happening. And again, the setup actually very similar, which is the same as here. Which again, you have your GR be pointing towards your sorry, this is not the correct path. Yeah, this one. Your GR instead will be the pattern, and this pattern will be pointing towards your count. So instead, you can see that now I don't no longer need the PC to be referencing my pattern for my local branch prediction pattern history table, because first of all, there's only one entry in this global register, which is just one big giant register, and I don't no longer need this pattern history table, which is like multiple entries. So you can see that now I just need one sort of entry be pointing towards my pattern. So again, I'm trying to emphasize that everything now is just, again, using a pattern. So this is the most recent. So it tells you that globally, I have a branch, I have a jump, 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 not jump, 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 not jump happening, and across all the code block. So this pretty much just indicates like another entry in your maybe 1110110 sort of sorry, not address. I have to emphasize on this. Yeah, this is some sort of address, but maybe you can sort of think of this as a tag in the cache design. I make that mistake. I'm sorry about that. Yeah. So yeah, because now that if you come to this, you might have to think that, oh, how many bit of memory do I have to set up? No, you actually just need a tag instead. So you can I don't know, maybe have 100 entries, like small type of entry, but like multiple different sort of patterns going on, and then have a tag associated with it. So you don't have to necessarily have to have that many giant memory to store every different possibility. So yeah, just make it like a cache type of mechanism will be fine. Yeah. So now I'm going to talk about something really interesting to conclude the idea, which is something called the tournament. Yeah, so it's going to be something called a tournament. But before that, I'm going to tell you about what's been called the index selection, and also what's been called the index sharing. So actually, very interestingly, if you actually look up, let's take up, let's look up Boom, and if I just take a look at so Boom is actually one of the schematics I really want to follow, and as you can see here, pretty much as you can see, in this pipeline, this is the different pipeline where you have multiple cycle fetch, and over here you have an instruction queue, which is what they do for register renaming and reordering, and also they have probably like I don't know, different cycles of different execution units, and which they have different cycles. As you can see now, I have suffering from a much more higher branch mispredict penalty. So in 5-stage pipeline, it's only like 1 or 2, and then the only thing is that if I have multiple branch misprediction, I add it up. But now this single instruction branch mispredict penalty also increases, so not that's bad. A few highlights that are actually happening here is, first of all, there's 2 stages of fetch, which is quite cool, because when you actually I'm not going to go into this just yet. I'm going to actually finishing talking about Gshare and also the BTP. So as you can see, this is one of the, I don't know whether this is actually standardized or industrial standardized, but Gshare is actually just this global sharing. Yeah, so global sharing is pretty much just before I'm going to introduce that, you're going to see there's something happening here. You're going to say that, okay, how come am I adding this sort of thing happening? So there's something called the aliasing. So what is aliasing? So say that if I have maybe you have remember that back to our local branch predictor sort of example, I have maybe a PC, and of the PC maybe I have two PC address, but both of them have perhaps the, okay, maybe I'll use the different results. 1110. Both of them have pointing towards a tag of this, and then maybe it says both of them points towards this. But maybe if I actually zoom in here, you can end up finding the pattern. It could be something like T T T N T T T N da da da. So I'm sort of capturing perfectly of my results. But perhaps for another one, it could be N N N T T T N N. So this is the actual result, isn't it? So if you can sort of think about this, then what actually happened is, when you have this sharing idea, because you have this pattern as your tag or as your index, now there is a significant problem going to be happening, which is, okay, if I have this 2N happening, when I do the update here, it's going to make it to become maybe 0, 0 or 0, 0, because during the update, it's going to tell you that, okay, mispredict once, mispredict 2. And then maybe over here, you will say that, okay, I try to bring it back by having another TT. So you're going to bring back to 1, 1 again. And now you can see that I sort of had this issue of sharing between 2 different branches. That only comes because I'm no longer using PC as my index. because now I just told you that, okay, I think the PC address might not be that relevant. I'm only using the pattern, but then pattern itself might share. So there's two types of issue that we can solve about this. First of all is that you notice that there's only 4 bits, and 4 bits might not be enough to capture the whole pattern. Yeah. So what happens if I just make it 6-bit? Maybe it will perfectly capture this, and then it will distinguish between these two cases because this is 4-bit and this is 6-bit. Maybe it will just capture like exactly the perfect like it just perfectly distinguish between them, because now I can fully capture the second case for the TTT case, and I can fully distinguish them. So as you can see, now it becomes 1 1 1 0 1 1, and that's different from 1 1 1 0 0 0. Or even just increase by 1 bit may be helpful as well. So one way to do it is like, how about if I have 1 more bit? That's helpful. But said that if we have already a lot of bit and we don't want to really increase another memory, so the other way of doing it is what you call the index selection. So like, what happens if you start mixing between your oh, sorry, actually, okay, sorry, I make a small mistake. Yeah, of course that you can just keep adding the bits, but now when it comes to the global predictor, the global predictor is already a register, and then it contains like multiple loops and stuff, multiple sort of loops across all the different possible branches within. Oh, sorry, this is not the code block, but yeah, you know what I mean, like the code block, and then there's like multiple branches happening. So there's multiple beats that are actually happening in my GR. So what happens is, if I can just use a bit of information about PC and just to like mix them up and then say that, okay, now I have PC as sort of distinguisher between two cases, like similar to these two cases. I want to have a distinguish between them so that they don't no longer share the same tag, and then to sort of contaminate between them, which is called the aliasing. So I don't want this contamination happening, and then I don't want like one of them to temper and then the other one to like try to recover, and overall it's like effortless. So instead, what I want to do is I want to sort of mix a bit of PC information into it, and one way to do that is by index selection. And to put it simply, you can do another one which is called the XOR, and then the XOR pretty much what you call the G sharing, so global sharing. So it's pretty much just a different bunch of stuff. And then in order to actually properly understand this, you probably need like, I don't know, maybe a discrete math sort of understanding about, oh, which one is better? Is it like by adding them, or is it better by XORing them? But probably this one is better because, first of all, Boom's using it, and the second one is because well, you suffer from like you need to have that much address sort of tag, isn't it? So if you have adding together, then is that the best idea, or can you prevent this by just using an XOR to prevent this collision? So collision is the word I'm going to use, because it's sort of similar to the when it comes to the hash table. You can sort of have the collision happening as well. So when you have the collision, that's the aliasing, and that contaminates the proper prediction I want to make. So yeah, that's pretty much the idea of the G-share. Yep. And then the final step is basically just having a branch predictor. And it's actually really, really easy to know between them. As you can see, I have like, I don't know, 2 different pattern history table, or maybe 2 different, yeah, so I have 2 different set. Maybe I have a local and I have a global. Actually, I forgot whether that's, okay, I'm not entirely sure whether I'm correct about this. But then if you have combining the branch predictor, it can be like 2 local branch predictor or something. Like you just have like, you can put like different strategy of branch predictor. But then which one is to take? So the easiest one is like, okay, what happens if I use another bimodal, just choosing between them? So if this is mostly accurate, then I'll use this one. Oh, sorry. If this one is mostly correct from bimodal, because bimodal have this hysteresis problem. So if this one is mostly correct, then I'll just use P2, right? And I'll, in the meanwhile, update the P1. So that's the idea. So if I can just have this bimodal, then I can pretty much have this device and second device, and I can have this updates between them, saying, okay, if P2 is correct, then I'm gonna reward P2 by minusing P1, or I can reward P1 by giving it 1 score, or actually no change. So essentially I can have 2 different devices, and between them I can both serve a request. And between a request, maybe I have a MOX. Oh, sorry, I'm going to draw this actually properly. So I can have 2 different devices, So I can have two different devices and both as a predictor, and they both have served this request, and maybe this give a prediction and this also give a prediction. And over here, maybe I have a MOX. And the MOX select bit, I'll basically having another third bimodal. Meanwhile, notice that this is bimodal, and this bimodal basically saying that, okay, which address are you looking at, or something like that. Okay, so I say, oh, this address is that. I actually don't know how you connect this together, but yeah, just said that you're gonna look up this, and then it's gonna say that, okay, it's gonna say strongly not taken, and you're gonna say, okay, I'm gonna select the results from my first device, and then just say that, okay, my first device is much more accurate in this specific point. So yeah, that's pretty much the setup as you can see. So again, I'll have address sort of pointing towards which sort of location am I looking at and which device is particularly useful. So that's it. And that's the idea about the branch predictor. But then actually, there's one more thing I really want to talk about. This is so far we talk about whether to jump or not. Okay, so we figure out the first problem, jump or not. But the second problem is, where's my address? My address is a big problem, isn't it? So if I want to know about which address am I pointing at, which address I'm going to, that's a problem. Because why is that a problem? Let's talk about let's take a look at the basic. Oh, actually, I have a very perfect diagram here, which I'm going to use later. Yeah. So if you take a look at not this one, not this one also, probably this one. This one's probably a bit easier. So I said that my installment of the branch prediction will be probably somewhere here. Again, I'm not entirely sure, but I probably I'll put it somewhere here, and it will fetch it into here, and then this predictor will somehow just like a machine and give it back to my PC. So instead, I'm going to install this, have this installment. But then the happen is here, you somehow oh, sorry, I have drawn something wrong here. So this over here, it will give you like jump or not. So instead, this thing is actually a control signal. The control signal to tell you whether to jump or not is actually just basically controlling this bit, which PC will give you the actual, which PC dashboard should be the actual address. But now my problem is, how do we generate the address? The address itself, right, is pretty much just there's if you actually take a look at the oh shit. So if you take a look at the RISC-V branch over here, you can only generate that by having a PC plus immediate. So if you have this PC plus immediate, when do I actually generate that? It's going to be like in the execution stage, right? So yeah, we're back to our main problem. It's like, oh yeah, I know that I can jump, but then I still have to wait until like, so before we were waiting for like ALU to tell us whether we can jump or not. But then now my problem is that, okay, now I know I can jump, but then just when do I actually know that when I can jump? Like when do I compute this, right? And a solution for that is pretty much just having maybe I can do this early as possible. So I can do this in the decoder stage. Sorry about the diagram, it's a bit rough. But yeah, instead I can just do it in the decode stage. But that still doesn't solve anything, because that still doesn't solve the problem significantly, because as you can see, we still suffer from this problem where you have this bubble issue. So what happened was, yeah, I know I can jump, but then I still have to wait because I don't know which my address is, because my add is only happening after, isn't it? Because my immediate only come up after. So then the question is like, oh, how come if I just don't have this immediate starting to be decoded and just fetch into here? This is natural question comes here, but then it's very normal. Well, actually, I forgot the exact reason. It's probably due to the timing or physical constraint. It's probably due to the timing and critical path. But then, yeah, it's probably the main reason. But then, the idea is that instead you're gonna put something called the BTB. It's called the branch target buffer. So when you hear the word buffer, immediately think of cache. So if I have like some sort of cache-like structure, and if I have the cache-like structure, somehow if I have this predictor pointing towards here and it's pointing, and I have this cache just sort of fetch it back to tell you that, okay, this is my branch address. How nice is that? So if I just have the cache that store all the branch address I'm going to have, Isn't that kind of nice? So yeah, this is what the if you look back to the here when you have the G share. So G share basically tells you that, okay, I'm going to jump, and BTB tells you that, okay, you're going to jump. What's your address? I'll provide for you. So pretty much that's pretty much the idea. So as you can see, this branch predictor tell you, okay, I'm going to jump. I'm going to fetch your address, and then over here you'll be like hashtag structure, and then you'll be a BTB. And this very point, it will give it maybe this very address, it will give you, and then give you the data, and then this data will pretty much tell you the branch address will be, and then it'll go back to the PC. And just a refresher on the cache, it pretty much just looks like this, and then you just give it some tag and then also the set and by offset, and then you give it like that, and then it'll tell you to hit or not, and then it'll give you the data with, in there as well. So yeah, one way, a direct map, or two-way. So yeah, that's pretty much the setup of the whole branch predictor. Hopefully will be helpful, and as you can see, if you're really interested in this, you can read about the paper and then have a read, and then it'll be quite interesting. You can also read about like the resources as well. Okay, thank you.